All right, here we are looking at a couple of additional practice problems regarding material from Chapter 4, Section 5, which is almost exclusively about sketching curves. And we're using a lot of different information, as we saw in the previous part of this video, and that harkens all the way back to a college algebra class, maybe. And so I thought we would go through a couple of additional problems and see what it looks like to use those tools and processes in order to get a better feel for what it would look like to draw some of these graphs. So let's look at this question. Here I'm using some problems that I assigned to my own students through WebAssign, and I'm not endorsed by WebAssign. In the previous video I was using Stewart's, or some notes that were prepared for Stewart's calculus book. I'm not endorsed by Stewart either. These are videos that I'm making for my students that I'm also making available to anybody else who would find them valuable, because that's what I do. I do math and I try to help my students move forward with their studies. So let's keep moving forward with these notes. We're considering this equation and we want to figure out the intervals of increase. Increasing versus decreasing means we need to take the first derivative, so let's take the first derivative. We'll call that y prime, and that is equal to, we take the exponent, multiply it by the coefficient, and get a 6. There's the x, decreasing the exponent by 1 leaves us with x to the first, minus 18 times x to the 0, which is a 1, so we've got 6x minus 18. We want to find the intervals of increase, so let's figure out where this graph is neither increasing nor decreasing. In other words, where it has a horizontal tangent line. In other words, where the first derivative is equal to 0. Add 18 to both sides, divide both sides by 6, and we get x equals positive 3. So this is where we have our horizontal tangent line. Or I should say it's when we have our horizontal tangent line. To the left of this x value, our function may be increasing, might be decreasing. Actually, I'm going to have that on my x-axis be 3. And I'd like to test a point with an x-coordinate of 2, and also test a point with an x-coordinate of 4 to see, in my first derivative, to see whether my function is increasing or decreasing on either side of this x value. This is atypical, but I'm going to use function notation, but call it y prime of 2. So we'll take the x value of 2, plug it into the y prime, or first derivative, equation. We've got 12 minus 18, which is negative 6, which is less than 0. Therefore, we can say that our function is decreasing. It's decreasing to the left of x equals 3. Let's just go right to it. Decreasing is what the second part of part A is asking. Everything to the left of x equals positive 3, that means all the way down to negative infinity, or from negative infinity up to positive 3. I have a feeling that when we do this evaluation with our test value of 4, we're going to get a positive value. Let's try it. 4 goes in. 4 times 6 is 24, minus 18 is positive 6. That's greater than 0. Since our first derivative on that interval is going to be greater than 0, we know the function is increasing over there. And if we relate that to the first part of part A, for all x values starting at 3 and going up to positive infinity, our function will be increasing. Horizontal tangent line when x equals 3. Since we're changing from decreasing to increasing, that change in sign of our first derivative indicates that we probably have a local minimum right there. And in this case we do. The only time when maybe you wouldn't is if you had some kind of discontinuity happening there, a hole or an asymptote. Those are the first two reasons that come to my mind that tell me why I wouldn't have a local minimum at that point. And the question of finding the minimum, in this case there's only going to be that one minimum value, and the x-coordinate of that point is definitely 3. And then we have to take that x value of 3, plug it back into the original equation in order to figure out the corresponding y value. So we have 3 times 3 squared minus 18 times 3 plus 3. Okay, as you know, arithmetic is not my favorite. Here I've got 9 3's. I'm taking away 18 3's, so I've got negative 9 3's. And then I'm adding 1 3, so I've got negative 8 3's. 8 times 3 is 24, sounds like negative 24. So 3 comma negative 24. This is a fill in the blank, so we're writing in negative 24. When does our minimum happen? It happens when x equals 3. What is our local minimum? Negative 24, the y value. There is no local maximum because there's nowhere that we're changing from increasing to decreasing. That would be a local maximum. We don't have one of those, so it does not exist, is what we were requested to enter. In case there is no local max or min, in this case there was no local max. Find the intervals where the function is concave up. Concavity means we're taking the second derivative. Our first derivative is 6x minus 18. Therefore, the second derivative, y double prime, equals 6. 6 is greater than 0. Notice that this value of 6 is not dependent upon x at all, so we're going to say that our second derivative, which is 6, is greater than 0. Positive means concave up for all x values. So the fact that it's greater than 0, concave up. Part C, the first part of it says, find the intervals where the function is concave up. It's concave up everywhere. So I'm bubbling in from negative infinity to positive infinity. You're just writing these down as notes. So again, doesn't depend on x at all. Y double prime is 6, which is greater than 0 everywhere, so concave up everywhere. This little circle with a slash through it indicates the null set, N-U-L-L. Well, by this point in time, most of you have taken statistics, so you're familiar with the word null. That's the null set or the empty set, sometimes represented as empty brackets. If you haven't seen those should line up. Of course, this digital pen is not perfect. Pretty accurate, but not perfect. Find the inflection points. An inflection point is where you have a change in concavity. We do not have any changes in concavity, therefore there are no inflection points. We did get to talk about inflection points in the previous, or the first part of this video, which is actually a separate video, part 1. So if you'd like to look at inflection points again, if you haven't seen that video, I do talk about inflection points there. Changes in concavity, and the place where you have a change in concavity. My cursor was on my head that entire time, that was terrible. The place where you have a change in concavity, for it to be an inflection point, your function has to be defined for that x value. Sometimes that happens, sometimes it doesn't. We saw instances of both in the previous video. Determine, so inflection points we have DNE. excuse me, determine the end behavior of the graph. And this is nice, we're given a hint. We're pretty much being told what it is that means. We want to know the end behavior means what's going on with the y values as the x values get really large in the positive direction and then separately in the negative direction. Our original function, 3x squared minus 18x plus 3. You could take and apply the limit to this statement. This equation is nice because we know that it's a parabola. We know that the parabola is concave up because the leading coefficient, the 3 on the 3x squared, is positive. So our parabola is concave up, and a parabola continues to go upward as it continues to get wider, which means that as x goes to positive infinity, our y values will be going also to positive infinity. As x values get really negative, that parabola is also going sky high. I don't know exactly where this parabola is. Well, the one thing I know is that I've got a local minimum at 3, negative 24, so that, on a parabola, is going to be the vertex, 3, negative 24. And so we can see that this is heading up toward a positive y value, or a y value of positive infinity in both cases, as we go really far left and really far right. And again, 3, negative 24 is the local minimum, which also happens to be the absolute minimum, and it's the vertex. And that's going to be very helpful as we are in this multiple choice situation trying to pick the correct graph, heading toward positive infinity here. As we go left and right, same thing happening here, positive infinity as we go left and right. However, this is the only one with the correct vertex, so that is the correct graph. And look at this. Here's our y-intercept. We could have figured that out. We could have gone through the trouble of finding x-intercepts. That would have helped us draw the graph even more accurately. But also notice concave up everywhere. So the idea is we're supposed to be using all of these facets and characteristics of these graphs, or of these functions, in order to draw a more accurate graph. This particular question didn't ask us for all of the details, but for perhaps a free response question by one of our teachers or instructors, professors, we might have to calculate those additional values. So we didn't have to do that in that problem, or calculate all of those values in that problem, but if you'd like practice doing that, please refer back to part 1 of the 4.5 video. In this question, this is not a polynomial. This is a rational function. And as we can see from these multiple choice graphs, so this question has us going right to the graphs, we're going to need a vertical asymptote. Look, all of these have vertical asymptotes. You probably saw that right away, though. In this equation, this denominator does have an x value that would cause it to equal 0. That is an x value of positive 3. So we're going to have a vertical asymptote at or when x equals positive 3. So these two graphs on the right-hand side are contenders. Notice this curve is sort of in the second quadrant. Sort of. Actually, none of it's in the second quadrant. That's kind of funny. But it's concave up toward the second quadrant. We could say that maybe. But look to the left of this vertical asymptote. This curve is concave down more toward the third quadrant. So that's a distinguishing feature between those two remaining multiple choice options. And let's go ahead and concavity is going to require us to take the second derivative. That's going to be kind of a pain. Maybe we could use the first derivative. Look at my asymptote here. Sorry, my tangent line has a positive slope. This tangent line, positive slope. This tangent line, positive slope. On the bottom right portion of the graph, positive tangent line, positively sloped tangent line, positively sloped tangent line. What about in our other multiple choice option? What about the slope of that tangent line? Oops, it's not tangent to anything. What about tangent to here? What about this one? What about this one? All those look like they're negatively sloped. So, let's start out by taking the first derivative. Good practice for applying the quotient rule. Y prime equals the denominator, x minus 3, times the derivative of the numerator, which is a 1, minus the numerator times the derivative of the denominator, which is 1, all divided by the denominator in parentheses squared. Let's clean this up a little bit. In my numerator, I have an x and a minus 3 and a minus x. The x's are going to cancel each other out, leaving us with a negative 3. In the denominator, same quantity of x minus 3 being squared. A positive first derivative means positively sloped tangent lines. Negatively sloped first derivative means negatively sloped tangent lines. Do we need to plug in some test values that are on either side of the x value of 3 in order to choose between our multiple choice options? In this case we don't. Often you do, but in this case we don't, by noticing this feature. Notice that our denominator is a quantity that's being squared. Anything that's being squared on the real Cartesian coordinate plane is going to be positive, or 0. Our numerator is always negative, so you've got a negative divided by a positive. That is always going to be less than 0 for all x values except for x equals positive 3, where we have the asymptote. So we would say that our function is decreasing for all x except x equals 3. Decreasing or negatively sloped tangent lines, that solves this problem. This is definitely the right graph. We could use this expression or this first derivative and take the second derivative. If we want to do that, you could use the quotient rule again, or I'm going to rewrite y prime as negative 3 times x minus 3 to the negative second power, and you could use that expression to find your second derivative. Exponent times leading coefficient, decrease exponent by 1, chain rule, don't forget to finish by multiplying by the derivative of the argument, that inner function. You should get positive 6 over the quantity x minus 3 to the third power. And the derivative of this is a 1, so times 1. That's not going to do anything. That would be your second derivative. Oh, let's look at it. Here the numerator is always positive, being a 6. The denominator, you're cubing it, raising it to the third power, which is an odd power, which means if the argument in here is negative, a negative cubed is going to be negative. Positive divided by a negative will be a negative. So if your x values are less than 3, then this argument, as I keep calling it, right, if your x value was 2, that would end up being negative, cubed, negative, 6 divided by a negative, negative. So this is less than 0, 4. X value is less than 3. And it's greater than 0 for x values greater than 3. If your second derivative is less than 0, it's going to be concave down. And sure enough, on this graph, which is the correct answer, Everywhere on this graph to the left of, or less than, x equals -3 is concave down. And everywhere to the right of x equals +3 is concave up. So we were able to use the second derivative to confirm that that is the right answer. And again, you could plug in the x value of 0, the y value of 0, finding intercepts, x and y intercepts. The domain definitely consists of all real numbers except for x equals +3, where our vertical asymptote is. I'm looking at my cheat sheet over here to make sure that I address all of the different characteristics of these equations that we were looking at in the first part of the video. A horizontal asymptote. Let's mention that. Coming in and looking at the original function, the original equation, what is the degree of the numerator? What's the degree of the denominator? Both 1. When you have a rational function where the degree of the numerator and denominator are the same, right? Exponent of 1, degree 1, degree 1. The equation of the horizontal asymptote equals leading coefficient divided by leading coefficient. The leading coefficient here is a 1. The leading coefficient here also happens to be a 1. So our horizontal asymptote will have the equation y equals 1 over 1, which is equal to 1. And is that the case? Looks like it. Horizontal asymptote has equation y equals 1. What else could we look at? Slant asymptote. We don't have to consider a slant asymptote in this equation because in a rational equation the only time you're going to have a slant asymptote is if the degree of your numerator is 1 larger than the degree of your denominator. But that's not the case here. Our degrees were the same. Local maximums and minimums, in order to see if that's possible, we could take the first derivative and try to set it equal to 0, except we determined up here that our first derivative is always going to be less than 0. So it's never going to be 0. So nowhere do we have a horizontal tangent line. So nowhere do we have the possibility of having a local max or a min. Interesting. And what else? Concavity we talked about, and that was it. That's the whole list. Intercepts, domain, symmetry. We didn't talk about symmetry. Just from looking at the solution graph, we can see that there is no symmetry about the origin, and there is no symmetry about the line x equals 0. No symmetry about the y-axis. There is, not that you would ever be asked for this, I don't imagine, this graph exhibits symmetry about what point? It actually does exhibit symmetry about this point right here, which is 3, 1. That's the intersection of the two asymptotes, the vertical and horizontal asymptote. And remember that symmetry constitutes being able to pick a point on one part of the graph, and this is how I describe it anyway. If I walked to this point and then walked that same distance again in that same direction, I would end up at another point on my graph. If you can do that for every point on the graph, then your graph does exhibit symmetry about a particular point. Usually we see the origin as the point of symmetry. But here that's not the case. You could go through both processes in order to test for symmetry about the line x equals 0, in other words the y-axis, or symmetry about the origin. That would be for even or odd functions. Even functions are symmetric about the y-axis. Odd functions are symmetric about the origin. I'm looking at this equation. This equation is very similar to the previous equation, except you're going to have two x values which cause your denominator to equal 0, which means you're going to have two vertical asymptotes, as we're seeing in these graphs, at plus or minus 2. You can take the first derivative and check to see whether it's on what intervals it's increasing or decreasing. I think that's worth your while. And then you could definitely take the second derivative and check to see on which intervals your graph is concave up or concave down. In the use of the first derivative, there are going to be some places where your first derivative is equal to 0. Now that means I think maybe we should do this one. How far in are we? Somewhere around the 25-minute mark. Let's have a look at this one. Let's go for first derivative. I'm going to calculate the first derivative with a little bit of a cheat. I'm going to take my original equation and rewrite it as the quantity, x squared minus 4 to the negative first power. That way I can use the power rule and the chain rule in order to take the derivative of this. So let's go for y prime equals, I'm going to take my exponent of negative 1, multiply it out front, keep my argument, x squared minus 4, decrease my exponent by 1, it becomes a negative 2, and then I have to multiply by the derivative of the argument, which is 2x. And we can clean that up, writing it as first derivative y prime equals, you can put the negative wherever you want. I'm going to put it in the numerator, negative 2x upstairs, and in my denominator I'll put the x squared minus 4 to the positive second power. Is it possible to make this first derivative equal to 0? Absolutely. How do you make a fraction equal to 0? You make the numerator equal to 0. What x value would cause this numerator to equal 0? Definitely an x value of 0. So y prime equals 0 when x equals 0. That's either going to be a maximum or a minimum. So if we go in and we start chopping up the x-axis and looking at different intervals where our function might be increasing or decreasing, what are the different reference points that we want to be using? We want to use as reference points not only the x values where y prime is equal to 0, but we also want to, I'm going to see if I could erase this highlighting. Oh, that's nice. I lost a little bit of the 2 there. We want to use that x value of 0, but we also want to use the x values that are causing the vertical asymptotes. So, where should we do that? Let's move down here a little bit. And let's look at x values that are less than negative 2, x values that are between negative 2 and 0, x values that are between 0 and positive 2, and x values that are greater than 2, and see whether we think our function is going to be increasing or decreasing on those different intervals. Let's pick an x value of negative 3 to start with. Plugging in a negative 3 into our first derivative equation, which is up here, notice that the denominator is always going to be positive because it's a quantity squared. In the numerator, we have a negative times our x value. So as we're testing values, if I'm going to test a value here at negative 3, an x value that's less than negative 2, I've got negative 3 times this negative 2. See, that's not even an arrow. Now it's an arrow. Negative 2 times negative 3 makes a positive. Positive divided by a positive, still going to be positive. Alright, so I'm making a little table. Y prime is going to be positive on that interval. If you watched the part 1 of this video, this process was done a lot more gracefully because it was printed up with a really nice printed table and all the factors were all lined up, and we could see CU for concave up and CU for CD for concave down. This one isn't for concavity, it's for increasing versus decreasing, but it still works. Okay, now let's take an x value from the next interval. How about -1? -1 up here times -2, still going to be positive. What about now an x value of +1? So an x value on this next interval, +1. +1 times -2 is negative. And positive x value times the -2 from the numerator is also going to be negative. So the only place where we have a change from our first derivative being positive to negative is here. We're changing from increasing to decreasing, positive sloped tangent lines to negative sloped tangent lines. So we're going again from increasing to decreasing. And what kind of a point do we have when our function changes from increasing to decreasing? Climbing up the hill to climbing down the hill, increasing to decreasing, that is a local maximum. And when does that local maximum happen? At the x value of 0. That's when the local max happens. What is the local maximum? We would have to take the 0 value and plug it back into the original equation. Y equals 1 divided by 0 squared minus 4. So the denominator is -4. You've got -1/4, or 1 over -4. I'm going to just convert that into function notation. Y of 0 equals 1 over -4. Doesn't matter where that minus sign or that negative sign goes. Could go next to the fraction, could go in the numerator. At any rate, this is going to be helpful in choosing the correct graph. We know that we have a local maximum at 0, -1/4. So one of the graphs that's on the left-hand side, it's either going to be this graph because this point matches, or it's going to be this graph because this point matches. That point doesn't exist on the other two graphical options. Testing for concavity at that point is not going to help us because both of those graphs are concave down at that local maximum. But if we look at this graph, we see that over here it's concave up. Over here it's concave down in the other graph. So if you are in a multiple choice scenario, figuring out the second derivative and then testing for a value like -3 or -4 as an x value would help you determine which of those two remaining multiple choice options is the correct one. You can go through and use the quotient rule in order to find your second derivative and then test some x values that are from these same intervals. Would we need to test all of those intervals? Not necessarily. Once you find your second derivative, you'll want to see where it's equal to 0 or where it's undefined. And I can't take this second derivative in my head, but I know that the denominator is going to be x squared minus 4 in parentheses to the 4th power, which means you are still going to have plus and minus 2 as x values that would cause your second derivative to be undefined. And so those are going to be two of the reference points or reference values that you'll use to chop up your domain, your x values. So you'll be testing an x value that's definitely to the left of -2, between negative and +2, and to the right of +2. And that's going to help you see concavity. Remember, if your second derivative is greater than 0, it's concave up. If it's less than 0, it's concave down. I'm not looking for slant asymptotes in this scenario. Local max and min we talked about. You're going to find the second derivative using the quotient rule and the chain rule, actually. Because when you take the derivative of this as part of the quotient rule, you're going to have to employ the chain rule and take the derivative of x squared minus 4 again. And asymptotes symmetry. Of our two remaining options, this graph has symmetry definitely about the y-axis. This one also has symmetry about the y-axis. So you could do the test, it looks like, determining whether or not f of negative x equals f of x is going to be true, because these two remaining options both exhibit symmetry about the y-axis. It's also not going to help you determine which of these two options is correct. However, at least you know that that test is supposed to pan out. So if you would like to try that test, it should test true or positive for y-axis symmetry. It should be an even function. Definitely. Take a negative number squared, it's going to stay positive. That's the only instance of that variable. Alright, I want to keep going and just look at one more, because I want to try to give you as much variety as I can here. The conditions that we have to meet in this question are fewer than they were in the previous one, so let's take a quick look at this one. We're at about the 35-minute, 36-minute mark. Sketch the graph of a function that satisfies all of the given conditions. This says that the first derivative is greater than 0 if x does not equal 3. I think I read this problem once before and was confused a little bit by the x not equaling 3 part. However, if the first derivative is greater than 0, just generally speaking, that means that our function is increasing. It should have positively sloped tangent lines everywhere, except for maybe at x equals 3. Let's look at the options. Oops. Here x equals 3, that still has a positively sloped tangent line. Here x equals 3, that's got a negatively sloped tangent line. That's not going to be our right answer. Here x equals 3, negatively sloped tangent line. Not our answer. And here x equals 3, positively sloped tangent line. Okay. And my tangent lines are positively sloped, looks positive, looks mildly positive. Alright, so that graph in the bottom right is a contender, very mildly positively sloped, positively sloped, positively sloped. Okay, so bottom left and top right are contenders. Now, the next sort of instance, or what word am I looking for? Condition that we have to satisfy is that, oh yeah, it's written right there. Thank you. Could have pointed that out. Where were we on that one? So the next condition we have to satisfy is that f has to be concave upward for x is less than 3. Here's our x value of 3. Is our graph concave upward over here? It is. And is it concave downward where x is greater than 3? It sure is. This graph in the top left is looking good. Oh man. This one also is concave up to the left of 3 and concave down to the right of 3. That's still a contender. Next condition. F has an inflection point at x equals 3. Yeah, the concavity is changing at the point where x equals 3. There's an actual defined point there. That's true. That's common between both of them. Right about there. So that's the inflection point, maybe 3, 3. And in the upper left graph, 3, 0. Both of those look like inflection points. Next condition says that the limit as x goes to infinity equals 6. Alright, so as our graph goes off to the right, are we approaching a y value of 6? I'm going to look at this graph, and I'm following along. My x values are getting bigger and bigger and bigger. My x values are getting really big, like right there, it's 10. The y value there looks pretty close to 3. Right? Doesn't that look like it's about 3? All right, I'm a little skeptical there. Oh, look at this one. I would say that our graph has y values that are approaching 6 as our x values go toward positive infinity. And as x goes to negative infinity, let's just solidify this one. Y value is going to 0. Does this look like it's heading off to a point that has a y value of 0? I don't think so. What about this one? Definitely. Look, our graph is cruising along, skimming along the surface of the x-axis. Y value getting closer and closer to 0. We have our winner, star for you. These other problems, you simply have to satisfy more conditions. Close inspections of your graphs. As irritating as these problems can be because they're kind of detailed, I think one of the benefits is it forces you to go in and make sure that you have a really good understanding of what the different notations mean and what some of the vocabulary means, whether you're looking for inflection points or asymptotes or evaluating limits at infinity or evaluating limits as you're approaching from the left versus from the right. You're looking at concavity, making sure that you stay organized in your mind as you're looking at these different intervals. I mean, just go and show a non-math friendly friend of yours this thing and you'll start to see them turn green, right? The fact that it's not making you sick means that you're in pretty good shape. If you're starting to turn green, then you definitely need to practice these. And that's the end of that assignment. So you can see what some of my students are working on. Hopefully you're working on something similar and this was helpful to you. If you're not one of my students and you want to submit some requests or something, I'd be happy to hear from you. Shoot me a message. Regardless, thanks so much for joining me. I hope this was helpful, and I hope to see you again in another video. Take care.